I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to Physics Matter monthly on live and live colloquia series. So this is episode number 50. So more than 4 years ago now. So we have initiated this series dedicated to physics for development. So the Physics Matter scientific expedition highlight the capability of major research infrastructure like the Sesame Light Source in Jordan, and it supports the developing community by enabling the global knowledge sharing. So explore our past recording on this different YouTube that you can find on our webpage, and participate to live questioning as well to our esteemed guests, and help us spread the word about this unique series. So last month, Dr. Luciano Mossa has enlightened us about the CERN remarkable 70 years journey and emphasized the significant as well contribution from CERN to the society, like for instance, the invention of the World Wide Web, which enable us to be here today and then to work non-stop as well from virtually anywhere on our blue planet. So this week, we have the honor to welcome the 2023 IUPAC Kennedy Reed Medals, so for the outstanding contribution and to the enhancement of physics in developing country, so alias Professor Malik Maaza, that you have here, so on the screen. So our panelists today will be with Andrea Lossi, the scientific director of the Sesame Light Source, which will be here only a short time due to another meeting. We have Alan Hurd as well from Los Alamos, and myself, Christina, who are the past chair of the Forum of International Physics for the American Physical Society, which is organizing this seminar, and Sarius as well, Wetler, who is with us, who will be also asking questions. So our guest today will be bringing much more light as well from South Africa live. So he's a UNESCO Africa Chair as well for Nanoscience and Nanotechnology, staff at the University of South Africa and iTambo Lab, which depends on this National Research Foundation. He is an H index and he has more than 32,000 citations. So really an important index of 104. So he is a fellow of various academies, including the African Academy of Science, the European Academy of Art and Science, the New York Academy of Science, the National Academy of Science of India, the Islamic Academy of Science, and the Royal Society of Chemistry in London. So he has, in addition, also from this IUPAP, so the International Union of Pure and Applied Physics Award in 23, he has also received more awards, like for instance in 2018, from the Kame Kumar Award for the Excellence in Science and Technology. In 2019, from the Galileo Galilei Award by the International Commission for Optics. In 2022, for the Vasconcelos Award for the Education, by the World Cultural Council in Hong Kong. So he has also received the presidential, the Order of the Republic of South Africa. So you have been architect behind many different continental and national ongoing platforms, including the African Laser Center, the African Material Research Society, the African Light Source, and the Nanoscience African Network, the National Laser Centers, among all others, and it includes as well recently implemented this National Laser Center in Africa Center of competency in enhancing the nanoscience and nanotechnology for the Sustainable Development Goal. So this is an honor to have you with us, and we will then, all of us, prepare a few questions that we can add in the question and answer box, or we can also, at the end of this 40-minute seminar, give you as well the microphone so that you can ask live your question to Professor Maaza. So Professor Maaza now, so the screen is yours. And your microphone should be on.
Yeah, thank you, Madam Chair, Prof. Christine Darve and colleagues. First of all, allow me to express my gratitude to the organizers and the IPS family as a whole for their kind invitation in inviting us to share with you some of our work that we are carrying out within the physical sciences at the nanoscale in Africa, in particular in South Africa. I wish just to switch off my camera just to ensure that a broad band would be more or less allow me to go correctly. Allow me just to share also my screen, colleagues. So the talk of today that I would like just to share with you, if you allow me to do so, is science, nanosciences and nanotechnologies for sustainable development goals, in particular science benefiting the society. This talk is given within the framework of the UNESCO, UNISA, Itamba Labs, NRF, Africa Chair in Nanosciences and Nanotechnologies, which is a partnership, a trilateral partnership between the UNESCO Place Fontenoy in Paris, the University of South Africa, and Itamba Labs, which is a national facility, an accelerator-based national facility of the National Research Foundation of South Africa. The outline of my talk, if time allows, is first of all, I give generalities on the nano materials or nano physics, and then go to some typical examples whereby applying this know-how of a body knowledge in the field of nanosciences with the core component is physics for a number of potential applications of nanophysics for health, nanophysics for agriculture, nanophysics for water, and nanophysics for energy. And if time allows, I would share with you more or less what we think would be ideal to pursue, of course, in Africa, in South Africa, but in Africa as a whole, but with our colleagues and partners in the north, specifically the Trieste system, the ICTP, CISA, and the TWAS and the OWSW, and of course now with the American Physical Society. Thank you so much. Well, within the framework of the UNESCO UNISA Itamba Labs Africa Chair in Nanosciences and Nanotechnology, simplified as UNESCO Africa Nano Chair, the idea is to be the voice of the African continent in the field of physics at the nanoscale, and specifically to try to enhance, encourage, and cement further the application of physical sciences as a core discipline in different other disciplines, being chemistry, physics, computation, name it, engineering, within the African continent in the different 5 regions of Africa. And well, it happened that since the creation of the Nanoscience African Network in Trieste, during the era of late Professor Galeno De Nardo, who was in charge of the international office, the ICTP Office for International Relations, we have managed to create the Nanoscience African Network in 2005. And since then, non-stop, we have trained a large cohort of PhDs and masters in the field of physics at the nanoscale. And also we have hosted a large cohort of early career scientists, postdocs, and senior scientists from different parts of the African continent who converged to South Africa, and also visited, of course, the ICTP in Trieste, and also used this number of facilities in Trieste. And well, when they have these fellows, once they finish their training with us, they go back to their home countries, whereby they have indeed created and initiated a number of physical or nanophysics programs in particular, and spread to other disciplines. Colleagues, this is more or less some fellows who have been trained from different countries, as you can see: Burkina Faso, Uganda, Cameroon, South Africa, Egypt, DRC, Botswana, I think, and a number of other countries, colleagues. And in particular, we have had a specific program with fellows from war zones countries, and that was in the past Rwanda and Libya. And also, not only limited to the training of postgrads, but also hosting early career scientists, postdocs, and senior scientists from different parts of the African continent, and also in partnership with some north in Europe and the USA in particular training. Well, of course, the gender equity is of a major compass for us. 50% of the fellows that we train each year are females and 50% are males. And we do respect at each time and each period, at each cohort, that ratio 50-50. It happened that colleagues embarking in that in this model, whereby hosting a large cohort of African fellows and colleagues from the north, it happened that the citation of our publications has been enhanced quality and quantity wise. And again, you see the per citations per years of publication published under the affiliation of the UNESCO Africa Nano Chair, or the Nano AFNET, which was created in 2005 in Trieste. In effect, the field of nanosciences and nanotechnology is not a revolution by say, but it's just an evolution which went from the coal industry to the nuclear, to the semiconductor technology, to the biotech, ICT, and then in the 90s it was nanotech. It was in 2000 exactly, the major funding came in from different perspective and different countries and different continents. And of course, quantum technologies or artificial intelligence would depend extensively on nano devices. So was ICT in the past somehow. So it is an opportunity for the African continent and the global South in general to embark in material science at the nanoscale, in particular with a core component as physics. According to the IUPAC and the IUPAC definition, any object which has a size, one of its size, smaller than 100 nanometer is called the nanomaterial. And if we stick with by that definition, if we consider a gold atom, the gold atom, its size around 1 angstrom, that is 0.1 nanometer, and therefore a necklace of 10 atoms of gold close to each other forms a size of a nanometer, and that is the basal size of DNA, living DNA. So you do understand, colleagues, why, the field of nanosciences is extremely important. And you would remember, colleagues, that in the past we were using these disks here to store our data, and it was very large, quite big in size, but with extremely low capacity. And it happened that within that time, we are moving towards USBs with a terabyte capacity, smaller in size, but high, massive in terms of density storage. And that is, colleagues, due to the fact that the chips or the region where we can now store the 0 and the 1 became at the nanometric scale. And in fact, it will be shrinking further somehow according to Moore's law, if we are capable to remove the heat generated within such nano chips. And colleagues, the term of nano was coined by Norio Taniguchi as early as the 70s, and it was Richard Feynman who proposed that the nanotech in the era of 2000 would really bloom and so on. And he was right indeed, because it's at the level in 2000 that we have started to be able to manipulate matter at the nanoscale, at the atom by atom, that is the atomic force microscopy, and then also to be able to observe materials at the nanoscale with the super high resolution, even 0.1 angstrom with some electron microscopy high resolution somehow from Jobin-Yvon. In effect, the nano was existing. The Romans were using it because they were mixing a glass with the sort of gold or silver. And in effect, what they were doing by mixing it, that silver in glass, they were forming nanoparticles of gold or nano silver. And the plasmonic response of this colloidal gold gives her that color of red or green or blue. It depends on. But also the field of the nanomaterials, they are as older than how can I say, the life on Earth, because the magnetostatic bacteria is a natural factory, and it produces inside its body iron sulfide or iron oxide nanoparticles, which form a necklace, which are oriented according to the magnetic field. So the field of nano materials is as old as living species on Earth, that is millions and millions of years ago. But the point is not how old was this. The point is basic natural systems were using and are using their nanomaterials somehow to orient themselves. And you would understand, colleagues, that natural system, they are extremely very effective energy-wise and temperature and pressure-wise. And that means that nanomaterials... Sorry?
No,
Can continue?
go ahead. Yes, yeah, we can hear. So it's just a microphone. Go ahead, please.
Okay.
Thank
So just saying that if bacteria use it at that level, that means nanomaterials are effective energy-wise and so on. So colleagues, what controls the nanomaterials? Well, first of all, if you take a nanoparticle, that is more or less, you can imagine it's spherical particles of the order of a nanometer. First of all, the number of atoms on the surface can be as large as the number of atoms inside. What does it mean? That means that the properties of materials are not governed by the volume, but by the surface and the surface coordination of atoms. One. Second, that the atoms on the surface, the 3D symmetry is broken. Therefore, the atoms on the surface would vibrate differently, and therefore thermal conductivity properties of nanomaterials can be enhanced or can be higher than the bulk one. Three, free electrons, if you take metal gold nanoparticles, for example, if we take nanoparticles of gold, free electrons are trapped in a quantum well. Therefore, they are scattered many times, and therefore they are in a quantum well, which means you would have localized states, and therefore the band gap can be tuned accordingly. And therefore the color, from optical point of view, the plasmon frequency of these nanomaterials will be tuned according to the size. And that's exactly what happens. The other parameter that controls the nanomaterials is that the high surface to volume. Just to get clearly how it works, imagine you take a cube of size L, that cube has initially 6 facets. Now, if you cut it in two, you will create 2 facets. Imagine you cut each half in additional facets and so on. You will have created new surfaces and so on. Higher is the cutting stuff, higher is the number of surfaces that you are creating. And therefore, if you cut in the X, Y, and Z stuff, you would have a large amount of small cubes. And these small cubes would have heavily, highly enhanced surface to volume. And therefore, the properties of this material in terms of chemical reactions or bio binding with the conjugated molecules will be extremely very, very high. And colleagues, I will not go through the details how it manifests itself. First of all, when you take gold nanoparticles, if a gold in a bulk is yellow, it stops to be yellow. It can tune, its plasmon frequency can be tuned from yellow to red to gray to green to blue and so on. And what you can do also is that you can tune that plasmon frequency due to this localization of electrons in a quantum well. It's truly a quantum well. It depends on the size, of course, but also on the shape, because in the shape you would have 2 plasmon modes, the longitudinal and the transversal one. And the same applies for silver and other metals. Also, the thermodynamic parameters are size dependent at the nanoscale. If a gold melts around 1,300 degree Kelvin at a bulk, at the nanoscale, it can melt at room temperature when it is extremely small. And this is more or less the law regulating more or less the melting parameter of gold or metals. It is related, of course, to the surface tension and so on. But it is here, how can I say, thermodynamic parameters, macroscopic ones, can be tuned size-wise. Other thing is that, well, all of us, we use cell phones, and the cell phones, the red color, the blue color, and the green colors that we see, they are not rare earth, how can I say, generated, but how can I say, if it was the rare earth, it will be not easy for everybody to have a cell phone. But in effect, we use zinc sulfide in our cell phones to generate these colors. And these zinc sulfides, they have different sizes. Higher is the size, bulky, smaller is the band gap, smaller is the size, higher is the band gap, and therefore you can tune the band gap optically, and therefore, colleagues, you will change the luminescence properties of these materials. So how can I say, the band gap, the electronic band gap for bulk material is really fixed, while in at the nanoscale it is quantized, and that is indeed given by a basic, truly basic quantum well. Also at the nanoscale, the shape you can tune it because the crystallographic growth thermodynamic is no more the one that we know for a bulk material for crystals, but you can force the growth of materials in some specific, how can I say, direction, because you control the surface tension easily. The nanomaterials, colleagues, you find them in different ways, either different particles, isolated particles, or particles in a host matrix, or thin films. Thin films, they can be in the, how can I say, in the longitudinal direction, can be centimetric or millimetric, but in the transversal direction, they can, how can I say, they have a thickness less than 100 nanometer, therefore they are nano. And also you can find them in a form of multi-layered systems for super mirrors, for X-rays, and for other optical application. You can find them also with the shape anisotropy, like the carbon nanotubes. I will share with you some of them, colleagues. And this is the, while here are, how can I say, graphics, here are the truth, here the real images of polystyrene nanospheres, and here is the nanocubes of platinum and here triangular nanoparticles of silver, and here cylindric shape anisotropy oriented gold nanoparticles, and here you have zinc oxide nanobelts, and here you have nanorods of self-assembled C6T, and here you have a multi-layered systems which is used for XUV mirrors in satellites, or such as James Webb. It does use such a kind of multi-layered systems. Colleagues, in terms of applications, colleagues, I will share with you, colleagues, some applications of physics at the nanoscale in different I will share with you, colleagues, some application in relation to some SDGs. I'm gonna start the one with the SDG 3, that is application of nanomaterials for health. Sorry, colleagues. Yes. So I will go and share with you, colleagues, some application in the field of nano health, very efficient indeed. And one of them is the usage of nanoparticles, bioconjugated nanoparticles for skin cancer treatment. I would like just to share with you a work which was done by these fellows, a PhD, a postdoc, and an early career scientist from different countries in Africa and Iran, life science, physical sciences, and DFT and molecular dynamic expert. So, colleagues, it happened that skin cancer melanoma affects quite a large community worldwide, in particular in the southern Africa, that is South Africa, Botswana, and Namibia. And it happened that there is a community, colleagues, in South Africa, and this community is called the Khoisan. And this Khoisan data shows that they do not suffer from skin cancer, melanoma. And well, if one do his or her homework, you will find out that in effect, this community does use this a natural extract of this plant that is called the Hoodia gordoni. And this Hoodia gordoni, they mix it with the goat milk and they put it on their skin. And colleagues, it happened that we tried to, how can I say, copy and paste somehow their know-how, their indigenous know-how. But what we have done is we used the natural extract of this Hoodia gordoni to bioengineer nanoparticles of cerium oxide. Cerium oxide is a class of cosmetics, but a really top range cosmetics. So we have synthesized, colleagues, nanoparticles of cerium oxide. As you can see, this is a high resolution electron transmission of a cerium oxide. Colleagues, you can see clearly it's the atomic planes here. And when you apply it, colleagues, when you investigate its optical properties, you will find out that this cerium oxide synthesized with this natural extract stops the UVA, UVB, and UVC. So we have had to characterize this optically speaking. So as you can see, this is the diffuse reflectance of this nanoparticles of cerium oxide. You can see clearly that has a heaviside type variation of the diffuse reflectance, and you can see clearly at in the UV blue region we cannot detect anymore. We have reached the limit of detection, and therefore the reflectivity here is 0. So is the transmission. Therefore, all is absorbed. So it stops the UV effectively. In addition, the cerium oxide has a low, what we call a ROS activity, which means here it's nearly 0 relatively to the ones that we find in the that we use, generally speaking, when we go to the bush or to the mountain or to the sea, and to coat to protect sunscreen, to coat to protect our skin. So you can see clearly the ROS activity here is nearly 0, and here it increases. What does it mean? That means when we put this cream on our skin, it does not affect the DNA because the ROS activity is nearly zero, which is not the case of the sunscreen that we use when we buy it from the pharmacy and so on, unless it's a low concentration. But here, colleagues, what we have done is that we have proven, or we have validated from physical science point of view, optically speaking, in effect, and the reactivity, photoactivity somehow in terms of ROS, the effectiveness of this indigenous knowledge. I would jump to another case, colleagues, or another community. It's called the Himba. And these Himba colleagues do live in the north of Namibia and the south of Angola. And these Himba people, colleagues, they are well known that they do not suffer any bacterial infection. Yet, colleagues, this community here, or these fellas, do not shower at all the way that we shower. They do not use water. Why? Because water is scarce. It's only for drinking. And yet, this community does not suffer any bacterial infection. And the work, colleagues, is done by these fellows from South Africa, from Sudan, from Botswana, and from Iran. These are computational and engineers, colleagues. This is a PhD in physical sciences. How can I say? A mathematician from Ames journal initially, and the life science somehow. So, colleagues, there is a problem of antibacterial resistance, and we know more or less the reason of these antibacterial reasons. I do not want to go that route, but we wanted to find out why the Himba do not suffer from the bacterial stuff. And in that regard, colleagues, these Himba people, what they do, they take red ochre. Red ochre is a rock. They take a specific type of rock, and then they crush it in a form of a powder. And what they do, colleagues, they mix it with a goat milk and make a lotion, and they will spread this lotion all over their body, including their genitals and their hairs, colleagues. And you will find out when you investigate this red ochre that they use, it's a nanoscale, as you can see, colleagues. Here are the cubic type, trapezoidal type nanoplatelets of, in effect, iron oxide. And it's at the nanoscale, colleagues. And when you do that, colleagues, you will find out when you investigate its physical properties, specifically the diffuse reflectance, you would see that, colleagues, it stops quite significantly the UV radiations. But colleagues, that explains why they don't suffer also skin cancer melanoma, yet they live in a very harsh atmosphere. The temperature of the sun can reach around 46 degrees Celsius during the day, colleagues, yet they do not suffer from that. The UV radiation is around 5%, but the DNI is elevated. It's 10 times the one that somehow in Europe, but they do not suffer from skin cancer melanoma. But something else, colleagues, you see that the reflectance of this lotion in the infrared region is above 50%. That does explain why this community do not suffer from skin burn, because this lotion stops the heat from the sun and reflects it back and protects their skin from skin pour les brûlures solaires. But colleagues, remember, we were mentioning that they do not suffer from any bacterial infection. In effect, colleagues, when you do bacterial testings in the life sciences, so in labs, you will find, colleagues, that specifically against the E. coli and the Staphylococcus aureus, these are the most bacteria which come if we do not wash. And colleagues, you would see that the activity of the red ochre can be highly elevated. It's not as elevated as the streptomycin, which is a reference man-made antibacterial, but the activity is not zero, colleagues, is nearly 30%, colleagues, while streptomycin is 40. Nonetheless, streptomycin is $100 a tube. And here, the red ochre mixed with the milk goat used by the Himba people in the south of Angola and the north of Namibia is 0.01 cent. So it speaks for itself, colleagues. Again, here, colleagues, what we have done using physical method and physics know-how to validate an indigenous knowledge from an indigenous community living in the south of Angola and the north of Namibia. Colleagues, I would like with you, if you allow me, just to move on to the application of nanomaterials and, how can I say, investigate extensively to produce nanomaterials for agriculture. One aspect, colleagues, is that, and which is related, of course, to SDG 2, zero hunger. One of the aspects that we have witnessed this recent years, in particular this year, and still last year, is the cost of food has been rocketed. Why is that, colleagues? Because the how can I say, the agri sector from all over the world do import fertilizers from the major suppliers, and the major suppliers is Russia and Ukraine. You would understand, colleagues, that because the war instability in that region, so the fertilizing supply is affected, and therefore the prices are rocketing too. So it is necessary to produce now fertilizers either locally. And in that regard, colleagues, these fellows have managed to convert, I repeat myself, colleagues, they convert the CO2 to nanoscaled carbonates. And these fellows, as you can see, PhDs from Botswana, female fellow, a fellow in the agri sector from the DRC, the Democratic Republic of Congo, from Egypt, and from South Africa, colleagues. These fellows came with the possibility. I will not go through the details, colleagues, because I will send this presentation to the organizers that they share with you. The point is, colleagues, these fellows, these three chaps have succeeded to produce nano fertilizers of calcium carbonate, of zinc carbonate, of iron carbonate, name it. And colleagues, these carbonates are very effective fertilizers. Just to give you an idea, colleagues, South Africa, which is a mining and agri country, has imported nearly $1 billion last year in terms of fertilizers. Yet, colleagues, the price we produce, we are an agri country, in addition to being a mining country, but the food has rocketed also. And therefore, why? Because this 1 billion fertilizer that we have imported. Therefore, we have to produce, how can I say, nano fertilizers locally. And we have tested these fertilizers, colleagues, on tomato plants. This tomato here plant without fertilizer, this is with a small amount, with an average amount, with a larger amount. The product of these colleagues is this. This is the tomato fruit that you obtain without fertilizer, with a small amount of fertilizer, a medium one, average one, and a larger below the threshold of toxicity, of course. And colleagues, you would see that the size speaks for itself. That means this fertilizer that was produced is effective. And colleagues, here, if I may come back to this, it shows clearly that a biophysical chemical process which was used to produce these carbonates have been investigated thoroughly using different techniques, including synchrotron, colleagues, investigations to ensure that, how can I say, these materials are not toxic, and how can I say, and their diffusion coefficient in a plant. I don't want to go through the details. The point is that physical method have been applied thoroughly to get to these results. The other one that I would like to share with you, colleagues, is related to water. And the real to speak about water, colleagues, is to share with you a graph. Of course, these are the fellows who have been driving this design engineering of nanomaterials with the physical methods or biophysical methods, are from Senegal, from South Africa, Egypt, and Iran, among others, colleagues. Just to show you how critical is this issue of engineering new materials, highly characterized, physically speaking, is this. This is the statistics giving more or less the level of water in 1990 in cyan bars, and in a dark blue is the level of water availability in 2025, that is next year. This is by the World Water Council as well as by the African Union and related institutions. And colleagues, you can see clearly that while in the past the level of water was very high, except in some countries, in 2025, number of countries will be under scarcity, and all of them in sub-Sahara will be under vulnerability. What does it mean, colleagues? That means in under vulnerability, which means that fellows or communities would not be able to clean themselves or to use water to clean themselves. While under scarcity, that means communities in a number of countries would not be able to drink, to have access to water. And therefore, we have to treat this water, wastewater. And one of the way to treat wastewater, colleagues, is to use photocatalysis. But generally speaking, we use the titanium oxide to clean water. Once we shower, there is a water going down. We have to get this wastewater and to treat it, to remove any contaminant and any bacteria and so on. But unfortunately, the material of choice for photocatalysis is the TiO2. But TiO2 has a band gap of around 3.1 electron volt, which means to activate it, you need to have UV radiation. UV radiation in the sun is about 5%. And if you use an artificial lamp, it's extremely expensive. Therefore, it is necessary to create, how can I say, an intermediary band gap within the TiO2, the standard one. One way to do it is to dope the TiO2, or how can I say, to mix it with another element. But the DFT and the molecular dynamic, but in particular, specifically the density functional theory shows that if you create defects in the TiO2, in particular surface defects, you would be able to generate such, how can I say, you are able to tune the band gap to move it from 3.1 electron volt to 214 electron volt to nearly zero. What does it mean? That means that if we create surface defects, we would be able to have a TiO2 which would be active at solar radiation, infrared, or visible light. And that's exactly, colleague, what it was synthesized. Instead to synthesize the white powder of the TiO2, we synthesized, or these four fellows from Senegal, Senegal, Iran, and Sudan, and South Africa, have managed to engineer or bioengineer using a biophysics method to engineer a black TiO2. And this black TiO2 is at the nanoscale, colleagues, as you can see. And this is extremely effective. This is the ESR showing that in a standard TiO2, there is no defect at all. There are no defects at all. It's a flat, the ESR signal is flat, while the black TiO2 that we have synthesized, colleagues, it is highly surface defective in terms of oxygen. Yet the Raman investigation of this material shows clearly that in fact it is an anatase type, but heavily affected by huge oxygen defects on the surface. And accordingly, then we have created an intermediary band gap here, which is sensitive to infrared radiation and solar radiations, which is really cost effective. And as you can see, colleagues, this is more or less the reflectances of this nanoscaled powder. The major aspect of it is this, colleagues. Here is water contaminated with methylene blue. Why we use methylene blue? Because if you decompose methylene blue in water, you would be able to decompose any pesticide used in the agri sector contaminating groundwater. So, colleagues, if you put this black nano TiO2 in this methylene blue contaminated water and you leave it exposed to light, solar light at certain moment, after 30 minutes, it becomes nearly blue, somehow shady blue. But after 2 hours, colleagues, it's transparent, and therefore the methylene blue absorbs, decomposes, it goes down clearly, which means, colleagues, you have decomposed at least 90% of this harsh contaminant in water. And therefore, colleagues, that means this bioengineered or biophysically synthesized, the black TiO2 is a very effective photocatalyst at a certain extent. And therefore, colleagues, it is worth of doing density functional theory as well as molecular dynamic to see clearly to design new materials. The last case that I would like to share with you, colleagues, is a material which is related to the Mott phase transition. Mott and Goodenough are Nobel laureates who got their work on phase transition materials, and one of them is the vanadium dioxide. Vanadium dioxide, colleagues, can be used as an effective material, smart material for control of solar radiation in the infrared region in particular. That would save, more or less, can be applied as a coating for smart windows and a green air conditioning. I will not go through the details, colleagues, due to time limitation. What is sure is that the heat, we are obliged to use air conditioning in our housings as well as in our cars, because the heat exchange is mainly due or through the windows, glass windows. And therefore, how can I say, when it's hot outside, how can I say, the heat from the sun, the infrared, are transmitted through the windows. When it is cold, we lose heat from inside to outside via the window. So it is necessary to have a smart thin film, smart material, which would have a phase transition, metal semiconductor. Metal, if it is a metal in the metal status, it would stop the infrared. Therefore, the heat, it will block the heat from the sun. When it is cold, it will be transparent to the heat and to the infrared. Therefore, the infrared would come in. What applies in a window of a house would apply in the car industry, of course. And of course, you would understand, colleagues, when you use these smart coatings or smart windows, you would gain energy-wise, because you would not draw energy from the national grid. One, and second, you will minimize the CO2 footprint related to the usage of that energy of air conditioning. So the idea, colleagues, is to take a glass window and coat it with the material, and that material is a vanadium dioxide, which has a first order phase transition, metallic to semiconductor, and vice versa. When it cools down, it becomes metallic. When it goes semiconductor, when it heats up, it becomes metallic, and so on and so on. And that phase transition is extremely very fast. In ultra fast transition is around 180 femtosecond. Simply said, I will not go through the details. These are the fellows from South Africa, Sudan, and Cameroon, and others fellows from Senegal who worked on it. Colleagues, simply said, here is a toy windows, a toy house containing a glass window, shining on it a lamp. Close to that window, and inside we have, and this lamp is halogenic lamp, which is 1.5 solar sun. Therefore, at this distance is the equivalent of the sun shining on a normal window. And colleagues, the temperature measured by the thermometer inside that toy house room is 42 degrees Celsius approximately. While the one colleagues with that smart coating of VO2, colleagues, in the same condition, the temperature that you are measuring is around 32 or 33 degrees Celsius, is nearly 9 to 10 degrees difference, colleagues. What does it mean? That means here, colleagues, you do not need air conditioning because that coating is intelligent. It flips to reflecting infrared heat when it's hot, and it becomes transparent when it is cold. And the colleagues, here is, of course, a toy house, but you would understand that the large coatings on a car or a smart windows that we have in our houses would be beneficial and would not, how can I say, would allow us not to use air conditioning, and therefore this is an green air conditioning. But colleagues, in addition to it, to activate this smart phase transition, first order phase transition material of vanadium dioxide, there is no need for any energy input at all. So all is mahala, tout est gratis. Colleagues, this material, you would understand, has a fantastic first order phase transition from a semiconductor to a metal and vice versa. This transition is 68 degrees Celsius. The point is you have to bring this 68 degrees Celsius to 25 degrees Celsius. How you do it? You dop or you control the size of these particles, or you design it. When you do optical calculations, you control the refractive index, the dielectric constant, the real and the imaginary part, and so on. It is possible, as we have seen, colleagues. And this material flips from a monoclinic to tetragonal and vice versa. And this phase transition, as I mentioned, is a reversible, a first order. It has been measured with ultra fast laser optical method, and it showed that the phase transition takes place around 180 femtosecond. Of course, colleagues, you would understand that it's related to optical band gap and so on, the splitting of the band gaps of the orbitals. I will not get that route. The point is, when it is hot, the optical transmission is low. When it is cold, the optical transmission in the infrared is very high. Voilà, c'est tout ce qu'il faut. That's what we should remember. Of course, colleagues, you would understand that this material cannot be used only air conditioning in cars and so on. It can be used in other applications, in particular the nanosatellites and the modern satellites for the James Webb, for example, also to control the heat, so to avoid damaging the electronics and so on, colleagues. I will go to the last case, colleagues, is the one which is related to to nanofluids. And colleagues, all of us are aware, and this of course related to SDG 7. Colleagues, I will jump this one, colleagues. I will jump this one also. I will just remind ourselves that James Clerk Maxwell, the father of electromagnetism, is well known for his treatise of electromagnetism. But he has not excelled only in that. He was the mastermind before everybody when it comes to the heat transfer. And he was the one who conceptualized the idea of nanofluids. What is a nanofluid, colleagues? Well, how can I say, the way of thinking of James Clerk Maxwell is to say the bulk of fluids for heat transfer have a low thermoconductivity, less than 1 watt per meter per Kelvin, as you can see, being it heat transfer fluids or organic materials. All of them is less than 1 watt per meter per Kelvin. But he has also mentioned that metals and their oxides, they have a thermoconductivity 2 order or 3 order of magnitudes. He said, what if we use small particles of these metals inside these heat transfer fluids. The thermoconductivity being an additive thermodynamic parameter, therefore the thermoconductivity of the nanocomposite will be certainly higher than 1. And that is the idea of James Clerk Maxwell and the nanofluids. Of course, it took place only, it became a reality only in 1990, when the DARPA, the Department of Defense and the Department of Energy and DARPA in the US embarked in nanofluids. Because in that time, we were not able to make nanofluids, which is not the case. And his treatment of enhancement of the thermoconductivity in the nanofluid is based on a Clausius-Mossotti approach of polarizability. So he showed clearly that the thermodynamic, the enhancement of the conductivity is the K static plus the Brownian, and the static one relatively to the standard fluid one is given by that. So which means if you optimize the nature and the concentration of the metal nanoparticles and their diameter inside, you will be able to enhance, to have an enhanced thermoconductivity. And colleagues, at St. Thomas, we believe what we see. These fellows who have been involved in this are from Iran, an engineer, from physics, and PhDs, master students from physics, from South Africa, Morocco, South Africa, and Iran, and other colleagues. What they have done, colleagues, is that they have synthesized the graphene in ethylene glycol. They have synthesized the nanoparticles of silver in ethylene glycol. Why ethylene glycol? Because it's one of the major heat transfer fluid which is used in the car industry. One, or as a coolant. Second, the graphene has the highest thermoconductivity ever in any material, because it has a thermoconductivity higher than the diamond, because the graphene is a diamond somehow, but sheet of diamond. In the silver, they have chosen the silver because the silver is the metal who has the highest and the largest thermoconductivity of any metal. So they have combined both. And colleagues, this is what, how can I say, when you synthesize silver nanoparticles grafted on graphene, this is what you see, colleagues. This is what you see. Here is the thermoconductivity, colleagues, measured from 25 to 45 degrees Celsius. Here is the ethylene glycol with around 0.325 watt per meter per Kelvin. When you take the graphene decorated with the silver in ethylene glycol, the thermoconductivity jumps to around 0.40. You may say, colleagues, 0.40 watt per meter per Kelvin is small. No, 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 no. C'est erroné. It's wrong. If from the engineering science point of view and heat transfer, it's massive. It's an enhancement of around 33%, colleagues. This is massive. And the applications, of course, are not limited to heat transfer, removal of heat transfer of any engine, but also industrial cooling, solar energy, nuclear reactors, geothermal, nanoelectronics, but data centers, colleagues. I will not go through these, colleagues. What is sure is the data centers, they generate a huge amount of heat, extensive amount of heat, colleagues. And you would then understand that the human society will be using extensive amount of data centers. So the idea is to, of Google, for example, in the case of Google in Singapore and in Finland, is to collect this heat from the data centers, to recover it and to inject it to the grid of the city, and therefore making green cities. Again, colleagues, this different application of physics in different fields have allowed us more or less, colleagues, not only to contribute to the body of knowledge of physics at the nanoscale, but it has enhanced a continental synergy, and in particular, bridging extensively with the Trieste system. For us, Trieste is the Mecca of science. For us, African, Trieste is the Jerusalem of science. And for us, Trieste is the Vatican of science when it comes to, how can I say, allowing us to access free to the literature and access free to the high value computational components. And in that regard, colleagues, I wish to express our gratitude on behalf of all the UNESCO chair fellows to those who believed in us, in particular the late Galino DiNardo and all the directors of the ICTP, Katipalis Srinivasan, and other colleagues from and other institutions from Sweden, from Germany, Canada, France, and of course the Trieste system. And I wish just to finish by this quote somehow from late Nelson Mandela. It always seems impossible until it's done. We never thought that we will be able to reach this level. We were at the 0 degree Kelvin. We reached 0 degree Celsius. That is with the help of the Trieste system. And I hope that we will extend our collaboration with the APS to allow us to move from 0 degree Celsius to 25 degrees Celsius. And I thank you for your time. Thank you so much. To you, colleagues.
Thank you so much for all those information. So connecting the knowledge, so from the nanoscale, but with this micro brain, I would say. So thanks a lot. Very, very interesting. So we had quite a question. So indeed, so we can maybe start so chronologically. So we had so one question from Stefan Situma, who was asking indeed when you were presenting the different aspects as well of those, I mean, yeah, for the cosmetics. So speaking about the gold mix, so it has been used as well for healthcare. So what does it make it as well so useful? How would you describe it, that it's suitable for the use?
What is sure is that when you embark in this kind of materials, you will find out the application are multifaceted. And for example, my knowledge, you would understand my knowledge in agriculture is at the bottom below the 0 degree Kelvin. But we have, as a physicist, we have to work with the agri people. And in cosmetics, we have to work with them. And they are the ones, they are the ones who guide us more or less at a certain extent. So what we do is that we embark in DFT, density functional theory, and find out if it applies to that field. And we take it from there.
Excellent. So maybe some new analysis as well to look at with that
Correct.
aspect, with the engine as well that you were showing. So the second question from Cave Mudedu was speaking about so the in vivo as well. So aspect, do you do any kind of nanotheranostics study?
Yeah. Well, again, I think the health aspect is not mine, but Karan Kluti and other colleagues from Pakistan and other parts of the world are interested, are expert in the field of. So we send them, or what we do is that we invite the fellow from them to come. We train him or her in the field, or we send them a fellow trained from our UNESCO chair to their lab. The bioengineer or biophysically engineer these nanoparticles and do the test that side. So we interface with different disciplines according to their needs.
Okay, so thanks for this answer. So another question, so from Tasafa Asakri, so asking as well from this nanotechnology, so where she's not exactly from, but she's from Ethiopia, and there is quite a large interest there. So I think she's wondering as well if there is any individual participation for advancing training opportunity. So looking at Ethiopia, maybe can you elaborate a bit on that?
Yes, it happened that the UNESCO UNISA Itamba Labs Africa Chair in Nanosciences and Nanotechnology is headquartered at the University of South Africa, UNISA. And it happens that UNISA is the unique higher education institution in Africa which has a campus in Ethiopia. And therefore, Ethiopian fellows are more than welcome indeed. And up to now, we have around 5 fellows from Ethiopia. And 3 of them have just graduated, knowing that before we have had a number of fellows from Ethiopia and Adigrat, for example, Addis Ababa, University of Technology, as well as IAU. So yes, there are possibilities. I think fellows can contact me. How can I say? They can look at Google and get my email, or they can see the first page, and we take it from there.
Exactly. So we'll put your email as well and your
Yes.
contact in the webpage so that I gave there. And indeed, I want to mention, so we had also from Tunisia, so from Professor Moussa Dabdi, who is also giving as well his email address in the communication, speaking about so the work that they are doing on the synthesis of new nanomaterial for energy storage and conversion. So it means that they could look as well for collaboration, and you can submit project as well. So to so this professor in Tunisia, we can add as well. So your contact there. So that would be nice. So indeed, possibility to exchange global collaboration. This is what we try to emphasize. And you had a lot of people listening throughout all the world, a lot in Africa as well. So it's impressive. So I'm trying to look at some of the questions, but in the meantime, Alan, so you have some question, Alan and Cyril.
Just one comment and a question. I mean, the comment is, of course, this is an exciting presentation showing the incredible breadth of science, nanoscience that's being pursued through ITIMBA and ICTP and of course, Professor Maaza's programs. My question is, what is the situation for commercialization? Are there any startup companies that have gotten interested in any of these technologies?
Thank you so much. That's exactly a hot point, and that is absolutely our target, the future target. So in effect, what we have done, our vision was, first of all, let's train youngsters and early career to reach a critical mass. So once we have, that was from 2005 up to 2013, from 2013 up to 2023, last year. And we said that by 2023, we would have reached a threshold of critical mass. From then, we have to embark in R&D translations. And that is the point. And therefore, once we embark in R&D translations, look for opportunities to have partnership with the industries and technologies and private sector. But also, we need to prepare our fellows in having an entrepreneurship type skills. Academia do not interface easily with the business sector. We need to prepare our fellows to have that attitude to, look at opportunities of R&D translation and see, use the same language as the private sector and embark in that. And we have organized with, in effect, thanks a lot to the IOP in the past and the ICTP, we have embarked with the Johnny Mela in that time up to now also to train fellows in entrepreneurship. And also we have embarked with the WIPO in Geneva to train our fellows in these entrepreneurship skills. But I think we are closer to come with something outstanding. I must admit, the technology that we came with, converting CO2 to carbonate, this is just outstanding. In effect, we copied Mother Nature, what Mother Nature does with the formation of coral in undersea and the mollusks and so on. That is exactly the model that we came with. And here, I think there will be quite a number of countries or partners who would be interested. But to respond to your, point, we are obliged to train our students. In addition to the standard academic training, they must acquire entrepreneurship type skills.
Very good. Thank you.
And in that regard, Alan, Prof, in that regard, the UNESCO chair has been upgraded last year from the U2 ACN2 from the UNESCO UNISA Itamba Labs Africa Chair in Nanosciences and Nanotechnology. 2, what we call ACCENT. ACCENT stands for the African Center of Competencies for Enhanced Nanosciences and Nanotechnologies for SDGs. And this ACCENT, in effect, it's the R&D translation wing of the U2 ACN2. And we would like to explore other possibilities, of course, of entrepreneurship with the IPS that we value, of course, and others. I hope that I responded to your points.
Very well, thank you.
Thank you.
So that's a critical and an important part to pass from the pure science to the application and through the entrepreneurship. So definitively. So Cyrus, so you had as well a question.
Yes. So first of all, I hope you can hear me well. Does that work? Yes, very well. So Malik, first of all, thank you so much for the talk, and it's good to see you, my friend, and good to see that you're well and that you're healthy. That's very important. So throughout your whole talk, there have been so many points, but one story that really stood out to me was the story about how they all the time already have used sun cover, basically, that they didn't know, you know, what the scientific ground is, but it was indigenous knowledge, basically, that has always been there, and there is scientific ground to that completely immerses into our scientific view. And I want to ask you, is that one of these examples that everybody is looking for, where indigenous knowledge is enhancing our science as we know it and really gives us new sparks of motivation and innovation? Because that is what everybody is looking for. Everybody is speaking to include indigenous knowledge into our system of knowledge and science. But I believe there are only very few examples at the moment where this is done very well.
Correct.
Very good comment. Very good comment.
In effect, how can I say, our communities, whatever the rural areas, whatever, they are an excellent experimentalist. In effect, each old grandmother or grandfather who dies is a library which is burning, which is dying. So we need really to get as much as possible of knowledge from them. Take the case of the Navajos in the US and the Indian communities in Mexico and Chile. We have to also remember that more than 73% of the pharmaceuticals, the modern pharmaceuticals, their origin is a natural phytocompound. And once it was identified, it was synthesized artificially. But yes, indeed, we need to link more with the indigenous communities.
Exactly, the diversity that makes it
Yes.
like in quantity and in quality, the richness as well for all the curing that you can get.
Yes, absolutely. And what you're doing by that, bringing this forward and putting this on the stage and spotlighting the science that is happening in Africa, I believe that's done way too little. And as we have been seeing today, there's so much science that should be shown and should be put more into the spotlight, especially in comparison to how much spotlight is the science of the Northern Hemisphere.
Thanks.
Exactly, that's the richness, the global south, and then those databases that can be created as well, the diversity once again. Yeah. So I will give the possibility to talk as well. So to Mohsen Marabi, who is raising his hand. So can you speak now, Mohsen? Maybe not. Mohsen, can you speak?
We cannot hear you right now.
Yeah.
You're unmuted, but maybe there's...
Yeah, I unmuted him, but and he seems to be there with a collaboration. But so we can try to bring you the microphone later on. So then there was some other question, if I remember. Voilà, looking at so in the chat, speaking about where was that nanoelectrode? Where did I see that? What can we expect as an application for nanotechnology on solar energy, especially in cleaning solar panel? So with a specific nanotechnology coating, so to remove the dust accumulation on solar panel in dirty locations such as in Africa. So what do you think about that?
Well, I think I can say in the case of the cleaning of the photovoltaics, there are indeed anti-fouling coatings and so on. But I think something which is really critical, and allow me please to go back and to share with you my screen. I think there is really something which is of a special interest. Colleagues, colleagues, here in the photovoltaics, indeed, one problem is the dust in the, how can I say, in the field. But another aspect which is more or less the effectiveness of a PV and a photovoltaic, if when it's heated, it loses its in terms of effectiveness. So its effectiveness drops with for each increase of 5 degrees Celsius, the efficiency decreases by 1%, which is huge. Therefore, it is necessary to cool a photovoltaic. Water, unfortunately, does not cool effectively the PV because the thermoconductivity of water is less than 1 watt per meter per Kelvin. The usage, however, of nanofluids will indeed make the removal, the cooling of the photovoltaics more significant and more effective, and therefore keep the rate of photoconversion very high. And that is in effect now communities, in particular Skatek, Norway, they are, how can I say, producing now photovoltaics with the nanofluid-based coolings. They are a little bit expensive because they use the silver nanoparticles-based nanofluids, while the idea is to use copper-based nanofluids. So yes, indeed, the application of the nano as a coating to remove the dust and to minimize the usage of water cleaning, there are anti-fouling coatings, but also nanofluids who would be definitely so effective in ensuring a high conversion for a long time. I hope that I responded to the question of the colleague.
Yeah, I think it was a very good answer. So for also the aspect of those nanoelectrode catalysis for the chemical synthesis, so do they, in terms of the production, are they kind of application as well? Can they aid as well the production of food and of hydrogen energy?
Well, I think, how can I say, nanomaterials by definition have a huge surface to volume. And when it comes to energy, water splitting or what others, this is a parameter of a choice, surface to volume, and minimizing or controlling the surface defects. There are quite a number. We from the UNESCO chair, we are not in that field, but there are quite a number of groups all over the world working in that. But we welcome these fellows who, how can I say, who are interested to, by that, we can welcome them in the chair. We will supply them with all the necessary, of course, and we will put them in a contact of experts in the field.
Indeed, the network, this is also the
Yes.
most important aspect as well, depending on the problematic. So another question, so from Maaza B asking as well, so the limit of nanomaterials and how you optimize the parameter during the preparation of samples, I would guess.
Well, in our case, there are, of course, for the synthesis of materials, you have physical, chemical methods, and the life science type methods. In our case, we opted for biophysics type approaches. Why? Because they are cost effective, and the methodologies that we are using, you operate at 1 atmospheric pressure and 1 at room temperature. So therefore, no need for a huge amount of infrastructure. In addition to that, we use natural extracts of plants as a very effective chelating agents, and that makes the bioengineering or biophysical approaches are very, very competitive.
That's this aspect and the competitivity that has to be enhanced. Super. So another question from Jess Sudnamulo speaking about, and from Uganda, asking as well if there is any connection or any office there in Uganda.
Yes, we have trained quite a large cohort of fellows from Uganda. One of them, the one who just graduated, in effect, 2 or 3 months ago, is Rashida Akoba from Makerere University, and also from, I forgot the name of that center. Uganda is extremely very well known in terms of agri. They are extremely robust in the agri sector. So our fertilizers will be more or less tested in life in terms of toxicity and biocompatibility in Uganda. Yes, there are activities in the field of nano there in Uganda. Not much, but there is.
For the university, so maybe we could also connect so the person
Yes.
with the university.
Yes.
So then another question from Agun Ibrahim speaking about the contaminated water, so with bacteria. So if you expose contaminated water with bacteria to nanomaterial in sunlight, for water disinfection, heat of sunlight will play a role, isn't it? So what do we know about disinfection result from heat or nanomaterial effect?
Well, photocatalysts are how can I say, are materials which are photoactive. Therefore, once you shine them with the solar radiation, in particular UV, they create highly oxidant elements. And these highly oxidant elements would destroy any bacteria or any pharmaceutical. What is sure is that the current trends are geared towards synthesizing graphite, and this graphite is very active. In effect, you produce this graphite from bio-waste or from plastic, in particular the PET, the plastic from the bottles. You can make this graphite, which is extremely very active and can destroy easily bacteria and contaminant molecules, pharmaceuticals, and others.
Very, very useful. So a question from Olumza Ajala, so asking, so if there is a way junior researcher in the field of nanotechnology can be helped to advance, so in the field of research. So maybe again, the address of the different places where they could apply.
Yeah, well, how can I say, we within the UNESCO chair, we have quite a nice sound footprint within the African continent. I do suspect our colleagues from Nigeria, the University of Nsukka, University of Nigeria Nsukka, as well as University of Obafemi Awolowo and the CRD in Obafemi Awolowo are really robust. They have capacities in that. But we from the UNESCO chair, we will welcome fellows, and not only we encourage them to work with their colleagues in their home countries, but they are also welcome to jump to us for 3 months if they are early career scientists, senior scientists. Also, we have a number of programs with within the chair itself, as well as with the TRIES system, the OWSEW, with the TRIES, with ICTP, and the TWAS. So we can indeed host them.
And that would apply as well to the question from Nanso Okoli, who is asking as well, so being also from Nigeria, so if you receive some mobility students, so the term mobility
Yes.
might be applied because he's a PhD researcher, so from Nigeria, but he's currently doing his PhD in nanoscience and advanced material at so the UFABC, which is in São Paulo, in Brazil. So with a focus on the perovskite, the solar cell. So same way, I guess it would be a nice way as well to combine knowledge across the South. So excellent. And we have, so no, this is the same hand raised from Mohsen. So maybe we'll give him another chance. Mohsen, can you speak? No. So then, Cyrus, I'm sure you have the microphone.
I have a microphone and I hope you can still hear me fine.
Yes.
So I have indeed two questions to Malik. One is that one goes to what we can do. So what is the thing, or what are the things that we can do to provide better resources to early career researchers in Africa? What do they need? How can we help them directly to give them a better hand to advance in their studies, to learn better skills? And also on the other side, what is the one skill that they should bring that will help them on their way to advance better as a researcher in the global community?
In effect, the ideal, Cyrus, the ideal colleagues from the North, first of all, thank you so much for each and all of you for having assisting us in that regard to reach this level. And that was worth of it indeed. As you can see, it was really worth of it. What is sure is that when the fellows graduate and so on, it's not easy for them to go back home and to find a place where they can be absorbed easily. And in particular, the idea is to have a seed fund for them, one. And when they go with the seed fund, the ideal is to have a basic infrastructure, just a basic one, because there is no need to embark in investing in a large equipment and so on. It's better for them to come. It's a mobility. So if we have a seed fund for them to have a basic equipment infrastructure at their home place, just a spectrometer, ocean optics spectrometer, that would be enough. But for high stuff, they need also mobility. And the idea is to create to duplicate the model of the chair regionally, not them to come to South Africa, but to stay in the region. Let's say Burkina Faso go to Senegal or Nigeria or Ghana and so on. So to ensure that to maximize the usage of local infrastructure, that's one, and ensure that there is still cooperation, at least a regional cooperation, to force the destiny for them, because I don't have an electron microscope. Let me, or an optical spectrometer operating from the range of 300 to 4,500 centimeter minus one. I have one, but the classical one, it works from 702. So I would be obliged to go to Ghana or Nigeria. If I do so, I enter in communication with the colleagues. So I create a synergy, and there is a confidence, mutual confidence and a mutual trust. And once we come with the, with the product, with a publication or supervision of student or a joint funding, that, it will gain a momentum. We need just a small seed fund and a mobility grants.
And then that could, with this critical path as well, give some good examples. So that should be maybe article written on those success story,
Yes.
and then to try to motivate as well with real
And Christine and colleagues, if you allow me just to add in, there is an outstanding idea that we managed to at least, have with the Canada, is a second life infrastructure. That infrastructure that has been used extensively in the north, and it's decommissioned and put somewhere in a corner. That equipment can have a second life and second chance if transported to this country. And we have done it with the Canada, with the INRS Canada. It works like a marvel.
So there is quite a lot that we could evolve on that as well, looking at even with the light source. I know that there are special campaigns looking at all those, so logistic as well. So combining so those different so network that we know, the people who own, the people that needs, the people that can transport. So I think that we could as well like give some possibility for developing more capacity as well in the different community that we know about. So we have another question from so Dr. Eric Mastika. So I will allow you to talk. Can you talk and ask your question? So Eric.
Thank you so much. Am I audible?
Yes, we can hear.
Oh, thank you so much. I really appreciate for the presentation. This has been amazing. Cyrus and Professor Malik spoke on what my question was. Because my concern has been, I trained in the UK, 2013, my graduation in University of Nottingham in nanoscience as the pioneer of the university. One of the things that when you currently I'm an academic staff at Kenyatta University in Kenya, but the I had wanted to really raise, is there a way that, which I've already said that Prof has spoken about it, a seed fund where in fact, one of the things that we've been thinking about with my supervisor initially is to think about, are there some of the small time equipments which such APC can be able to support us in a way to say this could follow the student, because after training in nanoscience, the struggle we have currently is that we cannot be able to characterize materials. We have to send them to Botswana, South Africa, or even UK and Japan. So if we can be empowered as a region, because we have the skills, we've gotten the best quality education from the West and the North. However, on return home, you realize that you go back to the test tube, which makes things even more difficult, because I appreciate that Professor Malik is aware that settling back can be difficult. So is there a way that such collaborations could enhance even provision of postdocs for some time? And how does one get to know about this? Because when I signed up for this, my interest is how do I continue enhancing in my nanotechnology, nanoscience education? Because I focus on hydrogen storage, carbon dioxide storage, but then on return, now I'm doing sustainable water for provision, because of course in developing countries, the difficult thing again is water. So these are some of the questions that ponders on return. Where do you start? You've got these skills, you have this knowledge, you can characterize, you can do the TM, you can do the ACM, you can do all sorts of characterization. But then you step back from and you realize, oh my God, all the knowledge acquired goes to zero. That means the investment actually does not cascade down. So my concern is, how do these platforms help us in our own perspective to build? Because I remember the words of my professor, Professor Martin Polyakov, who is a son, saying that, can we be empowering the Africans to develop Africa? And that would be my concern. Thank you.
Well, thank you so much, Dr. Masika. What is sure is that there are quite a number of opportunities or channels for such. For example, ISP, the International Science Program, Physical Science, is extremely robust, and he has been supporting Western, Eastern Africa and Central Africa for years. And in effect, if there is a photonic activities in Africa, it's because Uppsala University and the ISP program in particular. What is sure also is that there are possibilities through the IOP and the Royal Society in the UK. Well, if I may give just some typical examples, two fellows from one from Ethiopia, Dr. Zabib Nuru from Adigrat University, and what's his name, Professor Balangom from Senegal. They won 1.4 and 1.7 million pounds to create their own program and own centers in their home countries, in Ethiopia and in Senegal. There are opportunities. Let's work together. How can I say? I will be sharing my presentation with Christine, and you will see my email in the first page. And well, let us liaise, visit us, pay us a visit. We will invite you to come to visit us at the beginning for 3 months, you would see what we do and so on, and how you can carry out some experiments with us, some projects with us. And also in the same time, we will explore possibilities with either Canada or Royal Society, the UK, or other countries.
Excellent.
Thank you so much. Well appreciated.
Thank you.
Indeed. So happy that we can facilitate that, and maybe indeed we can collect at the same time. So that's something that the FIP could look at. So maybe Alan, and maybe with Cyrus potentially soon. So one related question, I guess, Cyrus, if you can.
Exactly. I wanted to tap on what you just said, and also what Malik and what Dr. Masika was saying, because Malik, you just mentioned that there's a second lifetime for a lot of devices, and having been blessed to study in Germany, where we have strong funding systems, and we have many laboratories that are filled with equipment that regularly get renewed. I believe that there's huge potential to also supply that, because what you just said, seed grants, that might be, that's always difficult to talk to funding, to talk to funders and get money from them. But it's not only about what you just said. It's not only about big light sources, like Christine was already thinking very, very big, which is amazing. But it's sometimes already about small spectrometers who make a huge difference. Now, I believe from what I heard, where the issue might lie is to organize that, to get equipment, because the equipment in the Northern Hemisphere that is towards the end of their first life and could get a second life is immense. So it's just a question of how to get it. So my thought and an idea that I would just love to throw into the picture, and then we can see whether that will be pursued, is that together with the APS, and especially FIP as the Forum on International Physics, we can work together to do a partnership program. There are many universities in the US that have huge laboratories. And if you have a partner university or a partner country in Africa as a big US university, and you know that your equipment that goes to a second life will, for example, be shipped to Nigeria or to a certain university in Nigeria, you exactly know where it's going, you know your partners, and you have always the same shipping address. So that you can partner up, and it will become very easy, because you know this spectroscometer goes out of lifetime. We contact our people in Nigeria. Is that something that you would like to have access to? Shall we ship it? And then the only cost that with which the US universities would support the program is paying the shipping to Africa. And then from there on, the African physicists, they can work with this equipment. So I believe maybe there's some ground with the APS and with FIP to facilitate that and talk to the American universities together with with the African universities, and find some bonds and some common partners there. What do you think?
I think this is a great idea. So indeed, it's to put this into the perspective of the limited fund or the type of program that the APS had. But I fully agree that it has to be tried. So we can maybe investigate this in January. I think that would be a very good way, and to propose this. And beyond that, for what I was mentioning as well, this current idea under development for the light source, but it could be as well for smaller equipment. So that could be as well an additional chapter in all the aspects. And this is to work as well with this RI Logistica, so which is capacity for this shipment. Because quite often the problem is the shipment, it depends on the law in the country, even to be able to receive it. So there are a lot of aspects that have to be taken into account. And I think this is exactly what Professor Maaza was speaking about, like this entrepreneurship. It starts as well at this level, if we want to develop locally as well this capacity and those different laboratories. But this is a perfect proof of a concept that could be, scaled up as well at the level of continents in one sense. So I really like this idea. So we'll take just one last question before we have to return to the line. So from Bashiru Hamza, so you have raised your hand. Can you ask your question really briefly? So Hamza.
Yes, hello, can you hear me?
Yes, we can hear you. So Yeah, so you have the microphone.
Yes, thank you very much, Professor Malik, for the presentation. We broadly welcome the idea. I think these are the initiatives we need globally, especially sub-Saharan Africa. In addition to what had just been spoken by Professor Masika, I am a graduate with a master's degree from Nigeria in nanotechnology. I have returned to Sierra Leone currently, but you find out that what all I have done in Nigeria, in terms of the equipment I use in the lab, in my research, and of course, I executed the research on electrochemistry using a nano material for the modification of a glassy carbon electrode, which is simply used for the synthesis of for the modification of an electrode leading to the production of for hydrogen energy and the redox environment from a small liquid organic molecules such as formic acid. So great ideas we obtained from that research, but now since I've returned home, you can't find this equipment any longer. So buttressing what Professor Masika just said, we need to have effective collaborations across the globe, down here to Africa, because I've seen people who have gone far from South Africa, Botswana, Cameroon, Senegal, and I formed the presentation slides. So if that can be extended to Sierra Leone and some other countries within Africa, I think that idea will be appreciated. Like if we can collaborate in a form of writing for grants, so that we solicit funds in terms of having access to equipment and some other research materials, so that we expand the idea of nanotechnology. I have a background in chemistry. My master's is nanotechnology from Nigeria. So there is a direct linkage. We try to connect these ideas on physics, chemistry, biology, the advent of computer science, all of these things. So from what Richard Feynman said in 1956, there's a plenty of room at the bottom, and as coined by Noru Taniguchi, all of these things. So as far as nanotechnology is concerned, there are lots to be done. You see, there are a lot to be done, a lot to be evolved from the concept and applications of nanotechnology. But
So
we from Africa have not benefited anything to the effect. We've just theoretically learned these things. That nanotechnology is XYZ very important, but we have not felt deeply the applications and how can we sustain this knowledge. And it's very important for like enhancing the sustainable development goals, linking from the ideas we get from nanotechnology in terms of energy, clean energy supply, water, health, medicine, all of these things. So I am pleading that we need collaborations so that we collaborate in terms of writing for grants, we embark on research from different countries, so that we begin to feel the impact of this nanotechnology in our respective countries. So
in your respective countries. So can I suggest indeed, because we will need to finish soon, so to write in one page, like all those different proposals, because then this is what we could look at exactly with what Cyrus was speaking about and with Professor Maaza to apply it. I really like what you point at, and we need to add more value in terms of the proposal to make it move forward and have possibility as well to have cases. So just please send us like a one page, maximum 2, if you have some reference in terms of what you would propose, what you would need. And with respect to the connection that I was mentioning before, we could certainly make something progressing.
Okay, thank you so much. I'm currently working on something, but I'm really happy for this opportunity. I will contact Professor Malik as you've just spoken.
Voilà,
Thank you. Yeah, thank you so much. I love this idea. Thank you.
Thank you very much. And I see that we have Professor Amadou Nwage, who is also raising his hand. So we have to give him the last word potentially. So Madoun, can you hear us? Professor Wage? Let's see, I asked to unmute, but can you hear us? And I can promote you to the panelists. Voila,
Okay.
we can even see you in theory.
Do you hear me now?
We can hear you now, yes, sir.
Okay. What I want to say, it concerns the so-called Second Life research equipment to be sent in Africa. You know, we have tried this scheme, but it doesn't work because the shipment could be very expensive, and also the customer, you have to pay. I remember we got an agreement with Lawrence Livermore National Laboratory, with Rutgers University also to send equipment in Africa, but it doesn't work. So what I would like to suggest is that to have a kind of agreement between American Physical Society and some African institution like Maaza Institute in UNISA or like some other institution in West Africa, to have a kind of sandwich program, a program similar to ICTP program in Africa or ISP program in Africa, where it is possible to train students to have some basic equipment to continue doing work at home. And I think that with maybe APS, this could be possible. I remember when I was the international counselor at APS, I've already made this proposal, and I think that maybe it could work if it is possible for APS to have agreement, a kind of MOU between American Physical Society or, I don't know, units of American Physical Society for collaboration with African institution or research institution. This is what I want to say. Thank you.
So thanks a lot for recalling that. So meaning that the next ALM, so annual leadership meeting, so we need to follow up on that. I think it's this is really good to see the continuity as well and the follow-up of any action if you already did start. But I would like also to add, and might be as well an interesting point, this ERI Logistica, so which is a possibility as well for all those custom fee and all those regulations to find way to waive it, because, and thanks to professionals that work on that. So that could help potentially as well if we add those different pieces of the puzzle to build up a nice image at the end from the puzzle. So we'll follow up on that. We'll follow up.
Thank
so
you.
Thanks a lot for the comment.
Thank you so much. Thank you.
And then I will, so we have now to finish, and I will simply mention while sharing my screen as well, because there was as well this African strategy that some of you may know for the fundamental and applied physics. So there as well for material, so that would be to answer one of the earlier comment. There could be as well connection network and people to connect with, and as well a question so for Maaza, or knowing the work that is ongoing with the graphene that you were speaking about, which is fascinating. That's really like a niche and a novel capacity as well. So with the work also from Singapore, so with so Professor Castro Neto, we had last but last time not, it was 22 in January 22, a really nice representation as well of what is ongoing there, and a huge team that they have that could potentially as well bring more capacity there. So are you connected with them? Do you work with them? Question, Professor Maaza?
Sorry, I don't think so, but we will definitely liaise and explore possibilities, definitely.
So this is perfect. This is why this network and this platform is really interesting to reach out. Okay, so then we upload again. So thank you very much for all your insight, Professor Maaza. And I will thanks everyone, but recall also that next year, so this was the last presentation of 2023, but next year we're going to start the International Year of Quantum. And for that aspect, so we will have in January, already in the premise of all of that, the possibility to hear, so Professor Philippe Chomaz from CEA, and he has already given some TEDx so that you can look at in French, but he will speak about this second quantum revolution and the CISA computer. So this presentation will happen on the 23rd of January, because the last Thursday will be this ALM meeting, so where we will have possibility to raise the question that Professor Amadou Nwage was discussing. So remember and put in your agenda, so the 23rd of January at 10 a.m. Washington time and 4 p.m. in Europe. So thanks again to everyone for your attendance, and we really have the possibility to thank again last time, so Professor Maaza. So thank you very much, and we'll put everything online, the recording and the slide and your email address. So thank you, everyone.
Thank you.
Thank you so much.
Thank you.
Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye.
And happy end of the year. Let's stay tuned.